Hi, this lecture is Electric Circuits 3, or basically resistors in parallel. What we're going to look at here today is the difference between current and voltage for resistors in parallel. Again, we'll calculate equivalent resistance for resistors in parallel, similar to what we did for resistors in series, but the formula is going to be different. And we'll also be utilizing voltmeters and ammeters in class, so we need to understand how they work and what their impact on our circuit would be. Okay, so to begin with, let's just remind ourselves what resistors in parallel look like. Okay, resistors in parallel must be connected on both sides. So in the picture on the left-hand side, here's our two resistors, a 12 ohm and a 6 ohm resistor, and they're clearly connected on both sides. Okay, so right here, they're connected on this side, and they're connected on this side. Okay, the branch points or the intersections don't matter. On the right-hand side, they're connected on one side only with a branch point. So they're not in series because of that branch point, but because of this side, they're also not connected in parallel. So they're neither. Okay, in the last slide, we talked about Kirchoff's junction rule. And Kirchoff's loop rule is the second rule in Kirchoff's rules. Okay, there's only two rules, so it's not too bad. Okay, again, we won't be using the rules in class necessarily. I do expect you to know them. But from a mathematical perspective, we're pretty much not going to use them. We're going to be using simplified forms of these rules. Okay, so Kirchoff's loop rule is a restatement of conservation and energy. Okay, as an electron goes around any loop in our circuit, it cannot gain or lose energy. Remember, energy for an electron is going to be equal to Q times the voltage at that point. Okay, so QV is the energy, potential energy for my electron. And so as I go around any loop, okay, it must get back to the same energy level. Okay, or in other words, that voltage that an electron gains from going through a battery, it must lose all of that voltage or all of that potential energy as it goes through all the resistors in a loop. Okay, mathematically speaking, what we would say is that the voltage of the battery is equal to the voltage of the resistors as I go around the loop. Okay, this is a simplified form that we will be using for the sophomore year. We'll be looking at a little more complicated or more accurate form in junior year. Okay, so for resistors in parallel, okay, because as I go around a loop, okay, I might gain voltage, okay, going in this direction through the resistor, but then I must lose that same voltage going around this one. So it's exactly the same voltage, okay, going around my loop. So for resistors in parallel, the voltage drop or the voltage differential for each resistor must be the same. This is true whether it's resistors or other electrical elements, but we're focused on resistors. Okay, so the voltage in the equivalent resistor must also be the same. The currents, however, will be different. Mathematically speaking, what I would say is that the the voltage of all three of these resistors, my original two, V1 and V2, must be the same, and the equivalent resistance must be the same. So V1 equals V2 equals V3. This is similar to what we saw in series resistors where the current was the same. I1 equals I2 equals I equivalent. Okay. Notice, however, that the equivalent resistor in this case is 4 ohms. I'm not going to be adding my 12 and my 6. Not exactly. And so let's look at the formula and how we derive that formula. Okay. Again, Ohm's law basically says that the current through each resistor is equal to the voltage drop through each resistor. And because my voltages are the same, basically says that I1 R1 is going to equal I2 R2. Okay. So and the current through the equivalent resistor, okay, if I'm going to replace them, my current through the equivalent resistor must be the sum of my currents through the original two. This is similar to a restatement of Kirchoff's junction rule, Okay, if I'm going to replace them, I can't change my current. Okay, so in this case, the current through the equivalent resistor is the sum of the currents through the first two resistors. Okay, so substituting for I1 and I2 from Ohm's law, I basically end up with this formula that says the equivalent current is going to equal the voltage drop, delta V, times this fraction, sum of the fractions, 1 over R1 plus 1 over R2. Okay, and since that is equivalent to 1 over the equivalent resistance, I end up with my formula that says 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2, etc. Okay, and I must warn you, okay, be extremely careful when it comes to doing the math associated with this fairly simple looking equation. Although it's really simple, especially when you're doing it in the heat of a test, I've seen every single math mistake under the sun. Okay, so these are examples of things I see. Okay, people have come up and done, well, I have a 3 ohm resistor here and a 4 ohm resistor. And I do 1 over 3 plus 1 over 4, and I've seen people add that together and get 1 over 7. Okay, which is really silly because they forgot to add the top. Okay, so I've seen other people do 1 over 3 plus 1 over 4 equals 2 over 7, which is marginally better, but still incredibly wrong. Okay, and then I've seen people do 1 over 3 plus 1 over 4, and okay, they remembered that I needed to do greatest common denominator, and so they did, okay, multiply the top and multiply the bottom. Least common denominator, sorry, and ended up with 1 over 12, which is still wrong. Okay, and then not last, actually, I've seen more errors, but I've seen, this is a fairly common one as well, where they do make the formula that R equivalent is equal to 1 over 3 plus 1 over 4, which mathematically is correct as 7 over 12, but it was the wrong formula. Okay, the right formula says 1 over the equivalent resistance. Okay, so it really should have said 1 over that. So at the end, you need to remember to flip your answer. Okay, so it's not 7 over 12, it's 12 over 7, and that's the correct answer. Okay, so a lot of you will make these math mistakes. I'm sure I probably made them myself, which is why I hate fractions as much as I do. Just slow down a little and double check your answer. Okay, so here's 3 examples that I want you to do for practice. Calculate the equivalent resistance associated with these 3 networks, okay? A, and then B, and then C, okay? And just like we did on series resistors, C is the tricky one, okay? And then last but not least, we're going to talk about voltmeters and ammeters. Okay, voltmeters measure voltage, and they basically measure voltage difference between 2 points. Okay, usually those 2 points are both ends of an electrical element, a battery or a resistor or maybe a light bulb. And so it goes in parallel with the element because it needs to know what's the voltage on one side and what's the voltage on the other side. Ideally, the voltmeter will have infinite resistance and therefore no current will go through that voltmeter. Okay. Ammeters, on the other hand, measure the current through a single point. So what you do is you take that ammeter and you place it at that point that you are trying to measure the current. You can't place it inside or inside a resistor, so you could place it right next to that resistor to measure the current going through that resistor. Okay, and so the ammeter goes in series. Okay, and remember, everything in series has the same current. Ideally, the ammeter will have 0 resistance, so it won't affect the voltage between one side and another. Real-world ammeters do have resistance, however. Same with real-world voltmeters. They do not have infinite resistance. So just to summarize, okay, resistors in parallel must be connected on both sides. Don't focus on the geometry of the situation, okay? Instead, focus on whether they are connected on both sides. Okay, resistors in parallel have the same voltage drop, but different current. Conceptually, that's the most important thing you need to understand from this PowerPoint. Okay. Mathematically speaking, the most important thing is the formula that says the equivalent resistor for resistors in parallel is the inverse sum of the inverse resistances. Okay. And the equivalent resistor will also have the same voltage as the individual resistors. Okay. Last but not least, remember that voltmeters go in parallel with what you're measuring, and ammeters go in series with what you're measuring. Thank you very much.